Assalamu alaikum and welcome back to the Learn Daily Physics. So previously we've talked about the Bohr model introduction. I introduced you the Bohr model and we've discussed its postulates. So now our lecture is that I will tell you that how the radius in Bohr atomic model, how the Bohr told us that the radius for an atom is quantized. So today we are going to talk about the quantization of the radii. So let's move on. So first we have to understand that what is an atom. Okay, because we are talking about atomic model. So this is a Bohr atomic model. So we have to understand what atom is. Then we will talk about what Coulomb potential is, Coulomb attraction is, or the Coulomb repulsion is. So the atom mainly consists of a positive part called nucleus. This part is called nucleus, and then we have some negative revolving part here called electron. There are number of shells and number of electrons here in the orbits. Okay, so we just say that we have only one orbit, and okay, here we have some number of protons. Let's say that Z is equals to the number of proton. Okay, this Z is the number of proton, and this is the electron, and the charge on the electron is equals to E is equals to 1.67 multiplied 10 raised to power. If this is electron, let's say this is electron, it will be minus 1.67 multiplied 10 raised to power minus 19 coulomb. And same for this proton, charge on the proton. Let's say this was Q1 and this was equals to this, and this was Q2, charge on the proton is equals to E equals to 1.67 multiply same as this electron, but this one is positive. Okay, so we have understand this that if we have Z number of protons, then the charge here will be equals to ZE, or you can say that if Z is equals to 10, then we will multiply 10 here, because this nucleus contains 10 proton and the charge will be according to 10 protons, and it will be the multiple of this 10. So now you understand that what is an atom. So I've give you some introduction of this atom which we are going to use in our next derivation. So let's move on. So we say that Q1 is equals to ZE, the charge of the nucleus. I told you that the charge of the nucleus. This is Q2 is equals to positive E. Now because we are talking about the interaction, we are not considering the negative term, because we are talking about the force. When we will talk about the potential, we will say that it contains a negative sign. Okay, so for the force and for the simplicity, we are considering that the charge on the electron is positive. Okay, we are neglecting the negative term. Now the force between the Z of E is equals to, okay, the force between two charges is always given by Coulomb interaction, and this is the Coulomb force. The force exerting on the 2-point charges is always directed toward the product of their charges. You can say and inversely proportional to the square of their distances. Okay, so this is Coulomb's law. Force is directly proportional to the product of their charges and inversely proportional to the square of the distance between their centers. This is a Coulomb force, Coulomb interaction, and Q1, putting the value of Q1 and Q2 here. We can see that when ever, this is the force between, let's say that this was the force between electron positive to negative, and F is equals to Q of E, okay, and this is the positive charge. The electric field lines are toward the positive, from positive to negative, and this is the, say that the force which provides the centripetal force to this electron, okay. For example, this electron have some velocity here v, moving in this direction anti-clockwise, so this Coulomb force is providing the centripetal force to this electron, and this electron is revolving around this orbit, and to neutralize this Coulomb force, this centripetal force should equals to this Coulomb force, okay, because if this Coulomb force dominates, okay, then our radius will increase, okay. If this centripetal force will dominate, then the radius will decrease, okay. So both are neutralized, both are, you can say that both balance each other, and the radius remains constant. So let's move on. That so this is the centripetal for mvn square, because Rn we are saying about the, for the n number of orbit or for the n state, this Rn square and this is the Vn square. So centripetal force is equals to mv square over R, and this is mvn square over R. For a charge around the nucleus, F Coulomb is equals to F centripetal. I told you that these two forces will balance each other, and this Coulomb force provide the centripetal force. So this is the Coulomb force K of Ze square over Rn square is equals to mvn square over Rn. This Rn will be cancelled out with this square, and mvn square is equals to kze square over Rn. So this was equation number 1, 2, and this is equation number 3. Now we are multiplying half 1 by 2. You can say that multiplying 1 by 2 on both sides, then we have that the half of mvn square is equals to half of kze square over Rn. Okay, so this is half mv square, and this term is equals to the kinetic energy, and this here is equals to half kze square over Rn. So this is equation gives us the kinetic energy, and we name this as equation number A, and this equation is used in the next lecture or in the quantization of energy. We will see that if we can do that in this lecture, so we will cover that up. But this equation is important, and you have to keep this equation in your mind, because I'm going to use this equation when I'm going to quantize the energy. So now we are going to use our second postulate. In the second postulate, we have seen that mvr, we said that the angular momentum is equals to the multiple of this h cut, and mvnrn in the second postulate. In my previous lecture, I told you that how this mvnrn is equals to n h cut. So this v of n is equals to n h cut over mvr. From this we find out the value of vn, and putting this value of vn in equation number 3 here we put that value of vn, and when we will put that value here, our equation will be in this form. Okay, we will have an equation in this form. So now open up the square, and opening this square here, equation will be like this, and this square Rn will be cancelled out with this one, and this m will be cancelled out with this, and Rn will be equal to n square h cut square m k z e square. So taking n square and z square outside, because these are the two variables and every other thing is the constant here. Okay, h cut is a constant, Planck's constant, m is the mass of electron, k is a constant, also Coulomb constant. You can say that E is also the charge which is constant. So putting these values here for these constants, you can say that this is 6.6, and when putting these values, this will equal to 0.53 into 10 raised power minus 9. And as this is a radius, it will have the units of length, and it will be equals to n square over z. So this is n square over z comes out here same as it is, and this value is known as R0, and R0 is equals to h cut square over m k e. Okay, so this is R0, and this is also called the Bohr radius. So from this equation, we have seen that Rn is directly proportional to n square, and Rn is inversely proportional to the z, number of proton. So this tells us that radius is a quantized thing. Okay, so radius is not non-quantized. It don't have any continuous values. It will have some values which will be dependent on z and n. For example, we see that we have n equals to 2, so it will have radius for n equals to 2, it will have radius of n square or 4. We say that it, as R of n is directly proportional to n square, for n equals to 2, the R will be 4. For n equals to 4, the R will be 16. So this is a small analogy, you can say that, to understand. So now we can say that the radius is inversely proportional to z, which means that the radius of hydrogen have a smaller number of protons, so it will have, its radius will be larger than helium and then lithium, because they have, as the number of proton increase, their radius will decrease, because the number of proton, the attraction of the nucleus will increase on the electron, and it will make them shrink. Okay, and they will come closer to each other. The Coulomb attraction will increase and they will come closer. Now the second postulate, we are going to write that mvn Rn is equals to nh cut, and from that we are putting the value of this Rn from this equation, you can say, so name it as equation number 4. So from equation 4 we are putting this value here, and this value gives us that n square h cut square, and from this v of n we are going to calculate the value of v of n, and this v of n comes out to be this term, and this term is a constant term, and it also have some value. I didn't calculate that, but you can calculate if you can, you want to. You can put this value of k 9.1 multiplied 10 raised power minus 31, e 1.67 multiplied 10 raised power minus 19, and this h cut 6.637 multiplied 10 raised power minus 34 divided by 2 pi. So you can find out the value of this v naught. So the main thing I want to tell you is that this v of n have also a relation with this c and this n. So the relation of this v of n with this c and n is that v of n is directly proportional to z, and v of n is inversely proportional to n, principal quantum number. So as in the case of radius, we have seen that it have direct relation with n squared and inverse relation with z, but it have a, in the case of v of n, it have the direct relation with the z and inverse relation with n. So for that, we can say that as the z increases, number of proton increases, then its velocity increases, and this is the main thing that we have to understand. We will use in the quantization of energy, that how the radius increases. For we say that the radius decreases and the velocity increases. Okay, as the radius decreases, the velocity increases, and many other things for that will change. So for example, from this we can say that the hydrogen have the higher radius. Okay, but the greater radius it have, the lesser velocity it will have. As much as greater the radius will be, it will be the slower. Okay, so as smaller will be the radius, so as smaller will be its orbit, you can say its velocity will be more than the larger one, and that's what I'm trying to say. So I hope you understand the quantization of the radii. So in the next lecture, we are going to talk about the quantization of energy, and I hope you understand everything very clearly. So if you have liked my video, so give me a thumbs up and subscribe to my channel if you haven't subscribed my channel. So till then, assalamu alaikum, and thank you very much for your time.